All right, y'all. It is time to start. We are going to wrap up the last bit of material that you need for Friday's exam. So we're going through chapter 20.6, and then we'll finish 20, and we'll do a lot of 21, which is the last content that we cover for this semester, and that gets put onto our cumulative final. All right, so let's take a look at where we left off on Thursday. So here is like the book version of what we drew together on Thursday. It's a voltaic cell. We have now decided that when we do these redox reactions, which are all about the movement of electrons, we don't have to have our half cells or our physical components next to each other. We just need to connect them with a wire that allows for the transfer of electrons. So here we have zinc. Okay, and it's going to go from zinc solid, which has an oxidation state of 0, to zinc 2 plus. Okay, so it loses electrons, which means it's oxidized, which means that this half cell is the anode. Remember, anode by definition is where oxidation occurs. It sends electrons over to the other half cell where reduction happens, so the gain of electrons, which by definition is where the cathode is. In this case, it's copper 2 plus, taking those electrons and going to copper solid, which of course also has an oxidation state of 0. Okay, so we are given this balanced redox reaction. We don't have to decide who's gaining and who's losing electrons here because we already have the balanced reaction. All right, so we're eventually going to come to a place where we don't have that balanced reaction, and we have to make a decision on where the electrons are going to go. So that's part of today's goal, is to do that. Okay, so some definitions that we need to call out here. All right, here's just a summary slide of what do you need to know about a voltaic cell. You need to know and be able to identify the anode, where oxidation happens. I remember that because they're both vowels. And then oxidation is loss, so that's the oil in our oil rig mnemonic. Reduction is the gain of electrons. All right, so and then be able from there say what direction are the electrons flowing. To complete our voltaic cell, we have to have a salt bridge. Okay, we cannot just send electrons over and not balance charge. The voltaic cell doesn't work then, we don't generate any electricity and our batteries don't work. We have to connect the circuit and allow for a full transfer of charge in this cycle. So anions and cations, that salt bridge just has some salt sitting in it. So a lot of times in examples it'll be sodium nitrate. So our anions, I guess I wrote anions first. Our anions will migrate towards the anode where the electrons have left. So that replaces that negative charge that left from our electrons going over to the cathode. In turn, the cathode gets the cations migrating toward them to balance that negative charge coming in with those new electrons. Okay, so if we were to go back and annotate that here, well, it's already annotated for us. There's our sodium cation and our nitrate anion balancing out that charge. Okay? We can also make a comment on what's happening to these electrodes. So the electrode is the chunk of metal sitting in there that's where our wire is connected to transfer those electrons. Okay? In this case, for both of our half cells, the electrodes are the metals themselves. So that's zinc and this is copper. They don't have to be the metals. We just need something there to act as a conduit. But when it is the metal, those are getting involved in the reaction. So eventually, our zinc electrode decomposes. Right? Because we need zinc, we generate those electrons by converting zinc to zinc 2 plus. And so that metal is going to degrade. On the other side, in other words, it's going to lose mass. On the other side, copper 2 plus is going to deposit on our copper electrode. So I'd expect to see a mass gain on this copper electrode. Okay, we could also have just some metal sitting there that connects our path. So if it was platinum, for example, which is a very common metal used for electrodes, because it's not very reactive, then that will not change mass because it's just sitting there as a sort of highway for our electrons to move between half cells. Okay? So this is another way to ask a question. All right, so there's our quick review of voltaic cells. So take a second and work this practice problem. Okay, this is a type of question you might get on the exam. Okay, so I've given you a balanced redox reaction, and I want you to answer these questions about it. All right. So key to this question is when you read it, make sure that you note that I have a balanced redox reaction. I've done the balancing for you. I'm showing you which is being oxidized and which is being reduced. You just have to figure it out. So the anode, okay, that's where oxidation happens. So I'm looking for someone that loses electrons. Okay, again, I'm using zinc a lot, which is, we'll find out why zinc is often going to be at our anode. But here it is at 0. Over here it's +2. So the reaction at my anode is just zinc solid going to zinc 2+ plus 2 electrons. Okay, at the cathode, where are those electrons going? So I'm going to have chlorine. I'm going to look at it over here. Chlorine in the chlorate anion is, let's calculate it, each oxygen is -2. There's 3 of them, so in total that's -6. So each oxygen is -2. 3 of them, that gives me -6. The whole ion has to sum to -1, which means that chlorine in this case has to be +5. Okay, so +5 over 2 -1. So there's our gain of 6 electrons. So that's our reduction process. So if I was going to write out the balanced reaction at the cathode, okay, I'd obviously need to put in my ClO3 minus, going to Cl minus, but I'm going to balance this out, right? So I need to include my waters and my H pluses to make sure that this is a fully balanced reaction. And then lastly, I include that, hey, I need 6 electrons here to make this process happen. So here's my balanced half reaction for the reduction process that happens at the cathode. Yeah? So I want you to pull out and recognize what's happening at the anode versus what's happening at the cathode. I didn't have to do any new balancing. I just needed to add in, the only thing I needed to do was add in the number of electrons that would be in that reaction. All right, so does the zinc half cell, if it uses a zinc electrode, does it gain, lose, or maintain the mass as the reaction proceeds? Well, we see here that it's going to be at our anode, so we are consuming zinc. So we're going to lose mass on this zinc half cell. And then the chlorate half cell, that doesn't have a metal. I can't rely on something within that half cell, like one of those species can't be my electrode, so there's platinum there. And it's just passing along the electrons, which means that it maintains the same mass. It's essentially inert here. It's just there to pass electrons. Okay, so really importantly for these questions, you recognize that I've already given you the direction, okay? And that's because it's in the balance. Like I know who's gaining and who's losing electrons. Okay, now we're gonna move on to looking at situations where you don't know that. We're going to hook up any random pair of half cells, and you need to tell me which one is going to be the anode and which one is going to be the cathode. All right, and so for that, we're going to introduce this concept of cell potential. So one thing we didn't cover in this diagram that we've been looking at is that at the top there, it says that these two half cells, when connected, generate 1.1 volts. Okay, so we need to know how to calculate that for any half cell combination, and we need to be able to identify which half cell is the anode and which is the cathode. Okay, even if I don't show you the direction, even if I don't name it as the anode or cathode, you have to be able to determine it. That we're going to look at standard reduction potentials for all of these reactions. And essentially the idea is at the anode, okay, we're going to assign reduction potentials, which are potential energies essentially. And we say up here, here is our zinc solid. Our electrons are at high potential energy when they're on that zinc. Okay? They have spontaneously, they would rather be on the copper. So they, analogy here is that our electrons are at the top of the waterfall, and when we connect them to the cathode where they have the option to be on copper 2+, it spontaneously falls down. Okay, and that generates a characteristic voltage. In this case, it's 1.1 volts when we connect these two. Okay, so what are these cell potentials? How do we calculate this number? Well, just like we did for our standard delta G and our delta H and delta S, we are going to have a whole list of, not those, of these down here. Okay, so that cell potential, that's the 1.10 volts that we wrote, or that was on our last slide. That's measured in volts, okay? And we can talk about it as the EMF as well. Electromotive force. You might also see it like this. And it's joules per coulomb, so energy per charge. That's what a volt is. All right, so by definition, okay, if you are dealing with a voltaic cell, it is a spontaneous reaction. Okay? So a voltaic cell is by definition spontaneous, which means quantitatively that our standard cell potential, E cell dot, must be positive. Okay? This is the key to determining which is the cathode and which is the anode. Okay? This number must be positive for a voltaic cell. All right, and it equals the standard reduction potential at the cathode, so where reduction actually happens, minus the standard reduction potential at the anode. And that's where oxidation happens. So we are going to get a table of all of those standard reduction potentials for a bunch of different half cells. And then when we combine them, we know if we want it to be spontaneous, we need to combine them in a way that the standard cell potential is positive. All right, so let's look at an example of that. All right, so like I said, we have all these thermodynamic values tabulated. If you go to the back of your book, you will also get a bunch of standard reduction potentials. Okay, and that means that we are dealing with 25 degrees Celsius and 1 molar concentrations for any solution, or if there's a gas in our reduction reaction, it's at 1 atmosphere. So here, for example, you'd see copper 2 plus 2 electrons going to solid copper. That has a standard reduction potential of 0.34 volts positive. Okay, so that's in volts, and this is what I would call the standard reduction potential, and it is always written as the reduction reaction. Okay? So we get a whole table of these. Okay? And we list them. Again, these are all standard reduction potentials. Okay? And typically in the book, they will be listed from most positive to most negative. Okay? Just be careful that on the exam, we are going to switch around the order, or we potentially will. So just make sure you're not assuming that we ordered it like this. But we would see that if we wanted the standard cell potential to be positive, then we should use the more positive standard reduction potential. So the cathode is going to be higher up on this list, right? So we want this to have the more positive, or if we're looking at 2 negatives, the less negative value. And this will be the less positive or the more negative value. Doing that will ensure that the standard cell potential is positive and that it's a spontaneous process. All right? So again, notice that when I combine these two, so let's look at zinc and copper, because that's what we have been looking at. So here's copper, and here's zinc. Okay, copper is higher up on my list. Okay, that means it's going to be my cathode. Okay, and that is actually what happens. The reduction happens at this place, right? So I would have 0.34 minus a negative 0.76. That gives me 1.10 volts. That's volts. That is the number that is in our diagram from the book. If I had swapped those, right, if I had tried to make zinc my cathode, and so I had negative 0.76 minus 0.34, I would get a negative number. Right, I get negative 1.1, and I would know that's not spontaneous. That can't be the process that happens. So this tells me that here, I'm going to have copper 2 plus 2 electrons going to copper solid. And even though it's written like a reduction reaction, I now know that at the zinc, in the zinc half cell, at the anode, I actually have zinc going to zinc 2 plus 2 electrons. Essentially, this negative sign is doing some work for us. It's saying, hey, we're not actually doing the reduction there, we're doing the oxidation. So we're taking the negative of that reduction, which is oxidation, because it's just the opposite process. Okay? So the key here is to combine these two. If we're doing a voltaic cell, which has to be spontaneous, which means standard E cell has to be positive, combine these numbers so that they give you a positive value. Okay, we'll look at go ahead. That's only when I combine a copper and a zinc standard cell, like a copper and a zinc standard half cell. All right? And then the question is that we'll answer here, where did these numbers come from? And you might have noticed that one of them was 0, okay, and that is by definition. So these are not like absolute values. These are all values. This is the voltage that we get when we hook up any of these half cells to the standard hydrogen electrode, which is abbreviated SHE, so I call her she. So if I were to connect any of these, so let's say we're looking at this iron 3 plus to iron 2 plus, if I connected it, it would be plus 0.77. And I have just decided that this is 0, which means that my standard reduction potential, by definition, for the other reaction, for our iron 3 plus going to iron 2 plus, is a plus 0.77 volts. Okay, so let's look at this. When we make 2 voltaic cells with a standard hydrogen electrode, that is she, When I hook it up with copper, okay, then I would say, well, I know that if I want this to run spontaneously, this needs to be positive, so I must have a plus 0.34 minus 0. That is how I have defined. So this is the value that I get when I hook these two cells up. And I'm going to say this, by definition, is 0. So then my other half cell must be a 0.34. Okay? In this voltaic cell, this is not the reaction that's happening in my standard hydrogen electrode, right? It's the oxidation, right? At this point, this, by definition, must be my anode. So really what's happening there is H2 gas is being converted into 2H plus 2 electrons, okay? And if we step back and think about this more conceptually, what's happened is I have partnered the standard hydrogen electrode with another cell where the copper 2+, the other thing in that cell wants the electrons more. So it spontaneously takes them, okay? In the next example down here, when I partner my standard hydrogen electrode with nickel, it turns out that my H+ want those electrons more than nickel. And so when I hook them up, I actually get a negative voltage, a positive voltage, which must mean, okay, I'm going to have this as my definition, because I know I am generating H2 gas. Okay, so I get a plus 0.28 volts, but I know that this process is happening. So then I must be taking nickel and converting it to nickel 2+ and 2 electrons. This is what's happening at the anode. And I would see a generation of hydrogen gas in my standard hydrogen electrode. Okay, so the identity of your two half cells, which one is an anode and which one is a cathode, entirely depends on who they are partnered with, right? So in this case up here, my standard hydrogen electrode, that was the anode. But now when I partnered it with nickel, it's the cathode. All right, so to determine who is who, you can't memorize, oh, copper is always going to be the cathode, because you can partner it with something that has an even more positive standard potential. Okay? So this is very similar to the concept of acids and bases, where it's like, yes, this will act as the acid if it's with something more basic, but it could do the opposite if you had partnered it with something more acidic. All right, so here let's look at two examples. We know already that when we partner zinc with copper, okay, zinc is going to be our anode, and copper is going to be our cathode. I wanted this slide here because I want you to just be aware of this notation. So that double line there means that I've connected these two half cells, and my half cell notation is one vertical line there between my two species. Okay, so a zinc and zinc 2+ half cell is partnered with a copper 2+ half cell. So I just wanted you to familiar with that. And I know these assignments not only because we've already done this example so many times, but because that's the only way to combine these two numbers to get a positive value. If I had flopped them, I would have gotten a negative value. Okay, so there's our 1.10 volts. And now, but if I were to put zinc half cell with an aluminum half cell, aluminum really likes to give away its electrons. Okay, it has an even more negative standard reduction potential. Okay, so when partnered with aluminum, zinc actually takes those electrons. Zinc is down here now. Zinc 2+ is here and aluminum is up here. It's going to give those electrons to zinc. So now aluminum is my anode, zinc is my cathode. Again, you can do the math to prove to yourself that this needs to be, if we're doing a voltaic cell, it's got to be spontaneous, which means I need to make a positive number when I combine these two values. So negative 0.76 minus a negative 1.66 gives me a positive 0.90 volts. Okay, if I had tried to reverse that process, I would have gotten a negative number, and that would have clued me into the fact that I assigned them incorrectly. Okay, so this is my cathode. I am now reducing zinc, and I am oxidizing aluminum. All right, so do this example. All right, a voltaic cell is based on a cell, silver chloride half cell. I've given you the standard reduction potentials. I want you to write the actual reaction that happens at the anode. So I'm looking for an oxidation reaction. Notice that both of those are written as reduction reactions because that's standard. So you're going to need to flip one of them and then calculate the cell potential. Okay, I might start with B in this case because to identify the anode, sometimes it's useful to make sure that you're calculating a positive standard cell potential. All right, so I need my more positive value, so that's going to be my silver chloride half cell minus a negative 0.28 volts. So I should have a standard cell potential of 0.5 volts, which means that my silver chloride was my cathode. So reduction is happening there. My cobalt is undergoing oxidation at the anode. So if I want to write out the actual reaction, it should be cobalt solid going to cobalt 2 plus 2 electrons. Okay, yeah. Mm-hmm. So I know that this equation is actually the standard reduction potential at the cathode minus the standard reduction potential at the anode. So I know whatever is here has to be my cathode. Whatever the first term, wherever that came from, has to be my cathode. This second term has to be from my anode. If I had flopped them, I would have gotten a negative value, which is telling me that it's not spontaneous. And I would have set it up in the wrong direction. All right? So this is just by definition. My standard cell potential has got to be positive. You combine your two values in this equation, one minus the other, such that it is positive. I could do it the other direction. I just wouldn't have set up a voltaic cell. I would have set something up that I need to put energy into to drive it, which is not what we're doing right now in this part of the chapter. Okay? So another thing I want to point out to you that you might have gotten tripped up on, which you probably didn't think about, but I'm going to say it anyways, is when I balance this reaction, if I wanted to hook up these two together and make a balanced redox reaction, I would have needed to multiply my second equation there by 2. Right? My cobalt provides 2 electrons, okay? But my silver chloride only accepts 1. So if I was going to write the fully balanced redox reaction, I'd need to add in a factor of 2 on that silver chloride, but that doesn't get factored into these standard cell potential processes. Okay, so when you make that calculation, I don't multiply by 2, I just use that value. And the reason is because those volts are joules per coulomb. So they both increase. Okay, so when I multiply by a factor of 2, my voltage doesn't stay the same. Doesn't change, it stays the same. Okay, so here's my balanced redox reaction. I have to multiply by 2 to make sure that I'm giving and taking the same number of electrons, but that has no bearing when we calculate the standard cell potential. It will come into play when we do non-standard cell potentials, but right now it doesn't. Okay, so just kind of a preview of where we're going. But right now I don't need to do that when I calculate E cell, that dot being the standard cell potential. All right. Okay, we're going to shift a little bit and talk about like sort of the qualitative description of these. So we often talk about oxidizing agents. You all know and remember that oxidizing agents are really good at taking electrons. They are the things that are more likely to be reduced. Okay, so when we look at this table of standard reduction potentials, the good oxidizing agents are up in this top left corner. They are the reactants in reduction reactions with positive standard reduction potentials. Okay, so these are the things that are just die. Oh, there it is. Taking electrons. All right. So I'm not going to ask you to memorize a list of strong oxidizing agents, but I expect you to know that if it is a more positive standard reduction potential, that means that the reactant on that side, so in this case F2, really, really wants those electrons. Okay, and then we can rank them based on that. Again, this is very similar to the chart that we had for the strength of acid versus the strength of conjugate base. If you're really good at taking electrons, then your counterpart, in this case F minus, is a really crappy reducing agent because it doesn't want to give those electrons back. Okay, so that means in the bottom right corner, so down here, when we're looking at the products of a reduction reaction, that's where our reducing agents are. Those are the things that like to give away electrons. Okay. Okay, so lithium and aluminum are down in that bottom right corner. Again, that means that lithium plus and Al3 minus are bad oxidizing agents. They don't want the electrons. They wanted to give them away in the first place, so they're not good at taking them back. So they're down. They're the products for standard reduction potentials that are very negative. All right, so a question might come at you like this, where I say, hey, of these three, rank them from the strongest to the weakest oxidizing agent. So the first step is to remind yourself, what does oxidizing agent mean? Okay, so I am looking for the things most likely to take electrons. So they want to be reduced. In other words, these would be the things that are likely to be at the cathode. All right, so I want positive standard reduction potentials, and I'm going to take the reactant. Okay, because if I take the product, those are things that have already received the electrons, so they wouldn't actually be good at taking any more. So I'm going to take chlorine, there's bromine, and there's iodine. Okay, so the right order is just 1, where I have chlorine. It wants it the most, because if I hooked up a chlorine and a bromine half cell, chlorine is going to take the electrons. Chlorine will be my cathode, bromine would be my anode. Okay, and then as we go down, iodine would be the least likely to keep its electrons of those 3. So now I'm flipping it, and I'm going to have you guys do this practice problem where now I want you to rank the strongest to the weakest reducing agents. Okay? Again, for a question like this, you will get the standard reduction potentials. So you don't have to memorize these. You just need to be able to interpret and follow this trend. So if you have your answer, show me 1, 2, 3, or 4. What did you get? Good. All right, so let's look at this together. I want the strongest reducing agent, the thing that is most likely to give away electrons. All right, so I see that's going to be down in the bottom right corner. And then, so don't lean on that because we might not give you this table organized this way. So don't rely on that. I need to find the thing that has the most negative standard reduction potential. Okay, so we're dealing with these three. So I want to pull, if they were all jumbled, I would find the aluminum reaction because it has the most negative standard reduction potential, which means aluminum is the most likely to give away electrons, right? So it partnered with any of those, it would be my anode, which means that it's going to be giving away the electrons. It's a really good reducing agent. Okay, and then next up is the iron, and then next up is the iodine. Remember, it might not be organized this way in a table, so just use your critical thinking and make sure that you are looking at those values, so the correct order is 3. Okay? So another way of phrasing this is I could ask you, I could say if I had iron 2 plus and I wanted to make solid iron, which one of these reactions, or I guess I could say which one of those reactants could I use to make this process happen? So which of the, let me write my options down here. So I could say which could be the reducing agent for this process. Okay, so could it be Al, Al3+, I2, or I-? Okay, so which of these could act as the reducing agent for this process? Okay, and so I'd say, well, I know I'm looking for something to provide electrons that is willing to give electrons to iron. All right, so I know, first of all, that it can't be something on the left side. I can't have something that is missing the electron. So it's not aluminum 3+, and it's not iodine. Okay, so it's either aluminum or it's I2, or it's I-. But then when I look at my standard reduction potentials, I see that if I were to combine Fe2+ with I-, that would not prompt a reaction. I- would keep those electrons and not give them to Fe2+. Okay, so the only thing in this list that would give electrons over to Fe2+ would be my aluminum. Okay, so that's just another, I'm gonna prep a question like this for you because I think this might be the more challenging way. Like, which one is capable of reducing Fe2+? And it is not iodine. The I- is not a strong enough reducing agent. Okay, if I were to hook these two half cells up, this would be my cathode, and this would be my anode. So I would not give electrons from I- over to Fe2+. Okay, it'd have to be aluminum. Okay, so we'll do a practice problem like that on Thursday, but just a little bit of a sort of reversal of the way you think about it. All right, we got to keep chugging. We got 2 more sections. All right, we already know that if a voltaic cell is spontaneous, I've told you many times already, it has to have a positive cell potential. Okay, so that means we already know something about spontaneity, right? What did we learn from chapter 19? We learned that a spontaneous process has a standard delta G that's negative. Okay? So if I am saying that it's going to be positive, a positive cell potential, but we already established that something spontaneous has a negative delta G, there must be some quantitative connection between these two variables, right? They are both indicators of spontaneity. We can connect them with an equation, which is what I've done here. Delta G, so that's our Gibbs free energy, equals negative NFE. All right, so E is the electromotive force, or the cell potential in volts. I've just written it, both of these, as non-standard, which is where we're going to eventually get to. N is the number of moles of electrons transferred in the balanced equation. This is why we do occasionally need our balanced reaction, because when I go to make this conversion, I need to know the number of electrons transferred. We'll look at an example. And then F is a constant, which you get on your equation sheet. Okay? So the Faraday constant is 96,485 coulomb per mole, or for these calculations, I would think about it as joule per voltsmol. Okay? And if we want to make this at standard conditions, we just add our dots here, which is then forcing us to be at 1 molar or 1 atmosphere. Okay? But we are eventually going to connect to those non-standard conditions up here. All right? So you get this equation. All right? So we just need you to be able to interpret it and use it. So there might be a quantitative question here. On Thursday, we calculated the standard delta G for our zinc copper half cell using just our enthalpy and our entropy values for those reactants. Okay? And we found that we had a really large negative standard delta G. Okay? That meant that it was spontaneous. Now let's see if that stacks up with the right standard cell potential. All right, so I just write in negative, well, let's write it out. Standard delta G divided by negative NF better equal our standard cell potential. Okay, so that is going to be negative 219 kilojoules per mole divided by, because I already have a negative here because our delta G was negative, negative 2. This value is 2. I look at that and I know this is a balanced reaction, and I am losing 2 electrons and gaining 2 electrons. So when this is balanced, there is a transfer of 2 moles of electrons. That's the N that I need to put in. So 2 is the number of electrons transferred when balanced. All right. And then I put in my Faraday constant, which you'd have in front of you. Make sure that you just use the right unit. It's in joules. I want it to be in kilojoules to match my delta G. So I've written it as 96.485 kilojoules per volt mole, and that gives me 1.1 volts. That's my standard cell potential, which we can cross-check. That is what we got when we used our standard reduction potentials. 0.34 minus a negative 0.76 was indeed 1.1. Okay? So we can now go between delta G and the cell potential. Those are connected. It's just that when we talk about these voltaic cells, we tend to talk about them in volts rather than kilojoules. Okay? But obviously, we have a relationship between them, which also inherently means that we have a relationship between the standard cell potential and K, our equilibrium constant, right? We connected, if we can connect these two, and we can connect standard delta G to K, then of course I could make a connection between, a quantitative connection between our standard cell potential and K. And I guess I'll write that down. I have our standard cell potential equals RT over NF times the natural log of K, or if I wanted to solve out for K, we could also write it this way. Okay? And then I just have a table summarizing all the sort of like big items here. If our delta G, our standard delta G is negative, that must mean that E is positive, which means that we have a K value greater than 1, which means that we favor products at equilibrium. And so the forward process is spontaneous at standard conditions. Okay? So remember, this means that we make more products. Down here, if we had a positive standard delta G, that would mean that E cell was negative. So that would mean a K less than 1. The forward process isn't spontaneous. In fact, the reverse process is spontaneous. So we would make more reactants. Okay? If it is a voltaic cell, by definition, we are dealing with that first row. Okay? By definition, that first row is a voltaic cell. Okay, so let's do a practice problem. All right, so I want you to calculate the standard free energy change and the equilibrium constant K using the standard reduction potentials provided for this balanced redox reaction. And while you're at it, you might as well assign one of them as the anode and one of them as the cathode. And think about what is the oxidation reaction that's happening. All right, let's look at it together. One thing I actually will point out here is that in this question, I don't actually state that it's a voltaic cell. I just say I've given you a balanced redox reaction. So you'll want to make sure that the way that it's written, just like you would, we'll show it, I'll give you an example. It is not, if I don't say voltaic, I could have given you it written in the non-spontaneous direction. In this case, I did. I wrote, well, who's going to be giving electrons? My silver gives electrons, right? And that would make sense, so that's going to be my oxidation process, which means that's my anode. And if this was my anode, then I am going to have a standard cell potential that is positive. I'm going to have 1.23 minus 0.80, and that is 0.43 volts. That's my standard cell potential that I can plug in here. But I could have, like, just double check. If you are given a balanced redox reaction, don't assume that it is spontaneous, especially if I don't write that it's not that it's spontaneous or that it's voltaic. Okay? So just double check yourself there. And then we have given those electrons over. Who's gotten them? Oh, our oxygen has gotten them. It's gone from 0 over to minus 2. So there they are receiving it. I just need to plug in now. My delta G is going to be negative, and my N in both of these, I don't need to add any coefficients. I'm giving 4 electrons the way that I've already written this. If it had been just Ag plus over to Ag, you would have needed to, in your mind, decided that you were going to multiply by 4. Okay? But that's got to be the balanced redox reaction. So there's 4 electrons. Okay? Our Faraday constant, which again you would have in front of you, is 96.485 kilojoules per volt mole times 0.43 volts, and that gave me negative 165.95. I'm going to call it negative 166 kilojoules per mole. So here's my G, okay? Yes, we all got that? Good. Hey, I could then take that and plug it in. I'm gonna calculate my K from the equation I wrote on the previous slide. I have K equal to 4 times 0.43 times Faraday's constant, which should now be 90. I'm gonna put it as 96,485 because I'm gonna divide by R, which is also in joules. So just make sure you're paying attention to your units here, times 298 Kelvin. Okay, and this is all up in the E here, so you wind up with a huge K. I got a 1.2 times 10 to the 29th. Okay, a really big K. In other words, this is a very, very spontaneous process, and we are going to make almost 100%, essentially 100% of our products and have no reactants left. Okay? On the next slide, here is the example I was talking about where I could give you a balanced redox reaction, okay, but I could have written it in the non-spontaneous direction. Okay, so here I have copper being oxidized and iron being reduced. Okay, so my standard E cell for how this is written is going to be negative because I've written it as the non-spontaneous process. Okay, so I'm going to have an E cell equal to, so this is my anode, and this is my cathode. So I'm going to have my iron, so negative 0.44 minus 0.34. Okay, so this gives me a negative 0.78 volts. I know that this means it's non-spontaneous and that I am going to calculate a positive delta G. Okay, so again, I'm going to have negative, my N is 2, because I am transferring 2 electrons. I'm going to use my 96.485 joules per volt mole and plug in negative 0.78 volts. Okay, so that gives me 151 kilojoules per mole. Okay, so of course, this is not a voltaic cell anymore, but I can do the calculation. So I just want you to be aware to look at that balance. If I could give you this question, even though it's not a voltaic cell, and I'd have to be doing something external, like providing a power source to make this happen. Okay? All right, we are going to go through now the same process that we did when we were looking at delta Gs, right? We started with these standard delta Gs. They're tabulated for us. That makes it very convenient. But we don't only ever run systems at 1 molar or 1 atmosphere. We often would like to do it at other concentrations. So how do we connect these standard conditions to non-standard conditions? Okay, that's our next step, and it's going to use similar math. Okay, so what we've been doing so far is calculating at 1 molar or 1 atmosphere, but we know, you also already have an intuition that these voltages must be changing. You all have used batteries to the point where they go dead, and that we don't have any more of our reactants, right? So our voltage must be changing as a function of concentration. So at some point we get to an E of 0, okay? So we just need to quantitatively connect. We need to incorporate the concentration of our reactants into our E equation. And again, we're going to do it starting from this equation that we've already looked at. Okay, but we're going to instead of delta G's, we're going to put in E's. Okay? So this should look familiar. We've got non-standard delta G equals standard delta G plus RT times the natural log of Q, which remember is our reaction quotient. So this is how we incorporate those non-standard conditions. Okay? Because Q is our equilibrium constant, that expression, but just at any concentration we would like it to be at. Okay? But now we know that delta G equals negative NFE, which equals negative NF standard E. So now that's how I'm going to make this connection. I'm going to plug in our value of delta G using our E cell. Okay, so I'm going to divide, we're going to go through and we're going to derive the Nernst equation, which is like the official name for this reaction, for this equation. Divide by negative NF. Okay, so we'll have E equals standard E minus RT over NF times the natural log of Q. We will recognize that these here, if at 298 Kelvin, which is the typical temperature, we're not going to do a lot of changing temperature in this section, we see that all of those are constants. Okay, so we're just going to wrap all of those into a number. And then we are going to, instead of being on the natural log scale, it is typical for the Nernst equation to be written in the log base 10 scale, which is annoying. Again, not my decision, but we'll make that conversion. And this winds up being E at non-standard conditions is the standard cell potential minus 0.0592 volts divided by N. So that number here, that 0.0592, that's our RT divided by F times a factor to convert from natural log to log base 10, log of Q. And then that V there is just telling you that we are getting units of voltage over here so that they match up with our standard cell potential, which is also in voltage. Okay. Now we have an equation that connects the potential of a cell at any conditions. So now we have expanded our freedom in calculations. Okay. We're not stuck at 1 atmosphere or 1 molar. All right. So we get that. And we'll do an example. Okay. So what is E? And now I'm not using the dot because I have different concentrations. Right? When I have copper 2 plus at 5 molar and zinc 2 plus at 0.05 molar. All right? And I have given you the standard cell potential already. Okay? So we'll have E equals, and I'm just going to follow this in, follow and fill in, 1.10 volts minus 0.0592 volts divided by, in this balanced reaction, this is balanced, you want to check that, but it is, we are transferring 2 electrons, so N equals 2. Then we multiply by log of Q. Now let's remind ourselves, what is Q? It is the K expression, so what we've been using all the way back from chapter 15. We don't include solids, right? We only include our aqueous species, so Q in this case is equal to the concentration of zinc 2 plus, our product, divided by the concentration of copper 2 plus. Okay? So I'm going to plug that in. 0.050 divided by 5.0. Okay. So when we plug those numbers in, the log here turns out actually to be -2. And so we end up adding that 0.0592 because our 2's cancel, so it is the minus. So this is 1.16 volts. So we've increased our voltage slightly by changing those concentrations. Okay. So there's this quantitative type of question, but then there's conceptual questions like, hey, what would happen to the cell potential if I increase the concentration of zinc 2 plus, or if I added in some zinc nitrate into the zinc half cell? So we are going to add, like, of course, at its core, that we could solve that as a quantitative question, but you might read it as a conceptual question because it's not explicitly asking you to do a calculation. But this is how you would answer that question. You look, what is it doing to my Q value, and how is that going to change E? All right, I have another practice problem for you, but this one is really similar to the one we just did, and I want to give you a different, like something more challenging. So come back to this one if you want more practice, but I want you to take a look, and you guys don't have this one, so look at this reaction on the screen. Sorry you don't have it in your slide deck. I've changed it over to zinc and aluminum. So there's going to be some ramifications because of how you have to balance this reaction, and now there are coefficients. So think about how that would impact especially your N and your Q. Okay. All right. Not that I expect you to have this completely done, but in the interest of time, we've got like 4 more slides left, and I really want to cover them today. So let's look at, I just need to fill in this equation, right? So I have standard E. I know, and I'm looking at this too, zinc is gaining electrons. That's my cathode. It's undergoing reduction. So this should be my first term when I calculate standard cell potential. I should have negative 0.76 minus a negative 1.66. That gives me a positive 0.90 volts. That's this value here. All right, and then I need to fill in this next term. Okay, so we know that's a constant. I'm going to divide by, okay, how many electrons are being transferred here? To balance this, to bring those 2 equations together, I needed to multiply my zinc by 3 and my aluminum by 2, because that's my lowest common denominator. I am transferring 6 electrons, right? That's the only way to bring these 2 together and balance them. That's my lowest common denominator. So I'd have, there's 2, but I've multiplied that whole thing by 3. You see that with the coefficients here, and I've multiplied this by 2. That's in my balanced equation as well. You could look at that and say, well, I had 3 zinc 2 pluses go to zinc that was 0. So in total, I must have transferred 6 electrons. So my N down here is 6. Then I'm going to take the log of Q. Okay, this is the other important thing to remember. I just find myself often rushing when I do these. Slow yourself down. You know that you should have Al3 plus squared because you have 2 of them, right? So don't miss that. Then you will divide by zinc 2 plus, which is cubed. Don't miss that, okay? So that is why I picked this one, because I just wanted to remind you that those coefficients become exponents in your Q. And so our log should be of our 1.5 times 10 to the minus 3. We square that, and then we divide by 0.55, which is cubed. When I punched all that in, I wound up getting 0.95 volts. Okay. questions on that? Okay. So that's the Nernst equation. Again, expect maybe something like this where it's just a straight up quantitative question. The other thing is, hey, look at our balanced redox reaction. How would you expect the reduction potential, or sorry, the potential to change as I add in these other things? So maybe it's increasing the zinc 2+ concentration or increasing the aluminum 3+ concentration. Notice that it doesn't matter if we add in more aluminum solid or zinc solid, because that doesn't have a place in our equilibrium expression or in our Q expression. So just that would be something that has no impact. Okay? All right, so I just have a summary slide here. The value of E at standard conditions, so this would be E obviously equals E dot, because our log would be of 1, which is 0, because Q is 1 at standard conditions. When Q equals K, this means we are at equilibrium. So E would be 0. Okay? We can't generate any more voltage because we are down at the bottom of the well and nothing is spontaneous anymore. Okay? So in that case, we're at equilibrium, and we could make that connection between E and K, which in the Nernst equation style looks like this. Okay? When Q is less than 1, okay, then the log of Q is negative. Okay? So then this negative here would make this whole term positive, which means that E is greater than E dot. And if Q were greater than 1, then the log of Q would be positive and E would be less than E dot. Okay, so that's just some sort of conclusions you can take from looking at that equation, from the Nernst equation. All right, and then our last little bit, concentration cells. All right, which we've already done all of these conceptual pieces. All right, we're just going to put them together. So imagine we have only been looking at which makes sense. We take 2 different half cells, right? And we're going to generate a voltage because one of these things, one of the species, wants those electrons more. That creates a potential that generates this voltage. We have electrons traveling in a circuit. We make electricity. Great. Okay? In a concentration cell, we connect the same half cells, which doesn't really make sense, right? If we were only looking at the standard cell potential, okay? That would not generate a voltage, right? If I connected 2 of the same half cells, my reduction potentials are the same. So the standard reduction potential, God damn it, the standard cell potential for a concentration is always 0 volts. That's by definition, okay, for a concentration cell. But we now know that if we play around with the concentrations, even though this is 0, we could generate a potential because log of Q will be a non-zero value. Okay? So that's what we do in a concentration cell. We hook up 2 of the same half cells, but we've changed the concentrations so much between the 2 that we generate a voltage. Okay? Remember, E dot is always going to be 0, and the voltage is generated from this term. This is the most important statement I can give you when you set these concentration cells up. This is like the reigning principle. The reaction will run until the concentrations are equal. That should make some intuitive sense, right? If I have a high concentration over here and a low one here, they don't run so that they're different. They run so that they meet in the middle. And that is how I want you to set up every concentration cell question. What needs to happen so that they are equal at the end of the day? All right? So let's look at a concentration cell. We're going to look at 2 nickel half cells, okay? But they have different concentrations of nickel. Okay, so in the left side, that's what my LS stands for, I have 0.001 molar. Okay, so I've got, we'll do some colors here. So here's my nickel electrode. and it's in solution. And in solution, I've got some nickel 2+. But on this side, my nickel 2+ is 0.001 molar. All right? On the other side, we have the same exact setup. And these electrodes in my pictures are in fact made out of solid nickel. All right? And again, we'll make it darker over here. Okay, we have a higher concentration of nickel 2+ over here. Okay, so here's where the principle comes in. Again, I want, at the end of the day, let's actually make it a voltaic cell, or a concentration cell. We'll connect them. We'll be thorough, okay? And then, of course, we have to have a salt bridge. Okay? All right, now we're ready to talk about it. Okay, I want, on the left side, if I'm gonna make these two equal, I need nickel 2+ to increase in concentration on the left side, right? And I need it to decrease on the left side. I don't remember what I just said. Right side? You guys, oh, and I'm looking at it the wrong way now. Okay, right side, we want the concentration to come down. We want it to come up over here. So, how do we do that? We have to look at our reaction, right? This is what's happening. If I want to make more nickel 2+ on the left side, then I better be doing the reverse. I need to be running the oxidation process over here. Because I'm generating, as this moves, as this goes on, if this is my oxidation process, I make nickel 2+. So I'm going to increase the concentration of nickel 2+ on that side. Okay? So over here is oxidation. Oxidation always occurs at the anode. This is how I identify that that is the anode. Okay, I have to make more nickel 2+ there. On the right side, I need to reduce the amount of nickel 2+. That means I should be reducing it. Okay, so there's my reduction process. This is, by definition then, the cathode. So I can now draw in my electron flow direction and say this is the anode and this is the cathode. Okay, I can calculate my E. Okay, this is, of course, this is going to be 0. I am always going to define Q such that Q is less than 1. That will mean that I get an E that is greater than 0, and it's positive, and that by definition, then this is flowing spontaneously. Okay? So to calculate this, I'm going to have E equals 0 minus 0.0592 divided by 2. I am transferring 2 electrons in my balance reaction. Then I'm going to have log of my dilute concentration, so that's 0.001 divided by 1. And that equals 0.09 volts. So a small voltage, but a voltage nonetheless. All right? The tricky part about concentration cells is that I cannot define the dilute side or the concentrated side as my anode or cathode, because that is going to change depending on whether or not my concentration is of an anion or a cation. So in this case, it was a cation that we were tracking. When it's a cation, the cathode is concentrated. All right? So I want to make this point. I'm going to use my last 3 minutes, and we're going to do this process again, but we're going to do it for where now I am tracking the concentration of an anion. But I have the same exact setup. On the left side, I have the dilute solution. And on the right side, I have the concentrated solution. So this is some other electrode. I've got a chunk of I2 sitting at the bottom here. Okay. And I've got I minus on the left side, and this is my dilute side. Over here, this is my concentrated side. All right, so to figure out which side is the anode and which is the cathode, I am going to say, what do I need to do to raise the concentration? I know that is the guiding principle. How do I make these two equal? Now, when I want to increase the concentration of I minus, that now means doing the reduction process. Right? Because my anions are produced in the reduction process. So now the left side, my dilute side, is where reduction happens, and that's my cathode. So it has switched from when nickel 2+. But it is, as long as you follow the process of what do I need to do to bring these two to equilibrium, it's not that bad. I need to bring this down. All right, what do I need to do? I need to consume I minus. That means taking 2I minus and making I2 and generating electrons. That's oxidation. Now my right side is the anode. Drawing a salt bridge here. Okay, so this is my cathode, which is now the dilute side. The anode is now my concentrated side. Okay, and we can draw in our electrons moving this direction. All right, so when you hit these concentration cell questions, write it out and ask yourself what reaction needs to happen so that these two concentrations meet in the middle. Use that as your starting place, and then everything else unfolds from that. On Thursday, we will do review questions for midterm 4. Look for those practice problems up tomorrow in Carmen if you want to do them before coming to class.